Welcome to The Explainer. Today, we're looking at how flyball governors control speed. We're going to completely unpack the mechanical magic that keeps our modern infrastructure, specifically the electrical grid, perfectly, flawlessly stable. Okay, let's dive right into this. Just picture this scenario. It's a sweltering summer evening, right? Thousands of people get home from work and boom, they turn on their air conditioners and appliances at the exact same moment. We totally take it for granted that the lights just stay on, but physically, that sudden massive draw of electricity places a literal physical drag on the massive generators producing our power. So, how does the grid prevent those spinning generators from instantly grinding to a halt under the weight of all that demand? The need for speed control. To understand the solution here, we first have to look at the physics of a single turbine driving an AC generator. Basically, a power plant is just converting the heat energy of steam into mechanical power. You've got high-pressure steam blasting through a turbine, spinning at absolutely incredible speeds. That spinning turbine is attached to a shaft, which spins the generator, and that ultimately converts mechanical torque into the electrical power flowing into your home. But here's the catch. This whole system requires absolute, perfect balance. And that balance? It's governed by this fundamental physical relationship. Generator counter torque equals magnetic flux times load current. See, the generator, while making electricity, exerts a physical counter torque on the spinning shaft. If the load current shoots up because, everyone just cranked their AC, the counter torque increases right along with it. This creates an immediate imbalance. Suddenly, the counter torque is greater than the turbine's driving torque, meaning that massive turbine will literally begin to slow down. Unless, of course, something automatically and instantly cranks up the steam flow to balance it all out. Anatomy of a flyball governor. Enter the absolute hero of our explainer. This is a simple yet utterly brilliant device designed to translate the rotational speed of the turbine shaft into direct physical action to solve this exact problem. It essentially acts as the automatic brains of the steam valve, and it does it all with zero digital computers. Now, what's really interesting about this specific setup is the anatomy of the Hartnell governor we're looking at here. You'll notice a central spindle, and that's driven directly by the turbine shaft. Attached to it are these bell crank levers holding heavy metal flyballs at the ends. And crucially, in this specific Hartnell design, we've got a central sleeve that's constantly being pushed down by a massive coil spring. Let's actually walk through this physical chain reaction step by step. 1. As the turbine speeds increases, centrifugal force throws those heavy flyballs outward. 2. That outward motion physically forces the mechanical levers to push the central sleeve, or collar, upward. 3. This collar moves up against that heavy spring, compressing it. And 4. This upward movement is physically linked to the steam valve, pulling it shut and choking off the steam driving the turbine. It's brilliant. And the true beauty is that the exact opposite happens when the turbine slows down. The centrifugal force drops, the spring shoves the collar back down, and the linkage pulls the steam valve wide open again to admit more power. Of course, the design we just looked at didn't happen overnight. It's the result of years of engineering evolution. Early on, engineers ran into a serious physics problem with designs like the classic Watt governor, which relied entirely on gravity to pull the balls back down. The issue? As speeds got higher, the gravity-based Watt governor basically lost its sensitivity. The sleeve barely budged even when speeds changed drastically. So they tried adding dead weights in the Porter and Proel designs. But eventually, they realized that for high-speed modern turbines, they really needed a restoring force they could precisely tune, and that led straight to the Hartnell governor, swapping out gravity for a heavy, tunable spring force that's compact and can easily handle the intense demands of modern power generation. The isochronous hunting trap. But here is where we run into a major complication in our narrative, because engineers naturally asked, hey, what if we design a perfectly tuned governor? One where the spring tension flawlessly balances the centrifugal force, meaning the machine always returns to the exact same constant speed, no matter the load. They call this an isochronous governor. Sounds ideal, right? Well, actually no. Trying to be perfect creates a massive, massive problem. That problem is a mechanical villain known as hunting. When an isochronous governor is mathematically perfect, its sensitivity is essentially infinite. It tolerates absolutely zero error. So when a load drops off and the engine slightly speeds up, this perfect governor panics and just sharply cuts off the steam entirely. But engines have momentum, right? So by the time the engine actually slows down, the governor realizes it overshot the mark, panics again, and blasts the steam valve wide open. The engine speed rapidly oscillates wildly above and below the target. It's this vicious, unstable resonance cycle. So looking at the causes of hunting, it's triggered by a combination of things. excessive sensitivity in the governor, insufficient mechanical damping to stop the oscillations, and rapid, frequent load variations. Now, if you just have a single generator supplying, say, one single factory, hunting is annoying. But what happens if you connect multiple, perfect isochronous generators together in parallel on a shared electrical grid? Oh man, they fight each other. One governor reacts a split second faster, hogs all the electrical load, and literally drags the other machines along with it, violently tossing megawatts of power back and forth. Honestly, it would be comical if it weren't so incredibly hazardous to the stability of the entire power grid.
Speed droop saves the grid. So, how on earth did engineers fix this? Well, by completely abandoning perfection. They introduced a highly counterintuitive concept that quite literally saves the modern grid. It's called speed droop.
So the crucial point is the contrast between these two approaches. Isochronous governing stubbornly tries to maintain a perfectly constant speed, which, as we saw, creates unstable hunting when generators operate in parallel. Speed droop, on the other hand, is an intentional design choice. It lets the engine speed drop slightly as the load increases. By not fighting to return to the exact starting speed, the governor doesn't constantly overcorrect. And even better, it allows multiple generators on a grid to independently vote on the system frequency. If the load increases, they all just naturally slow down a little bit together, sharing the burden proportionally without ever needing to communicate with each other. It's a real game changer. Typically, this intentional speed droop is set somewhere between 1% and 5% of the generator's full load speed. This tiny margin provides the absolute perfect balance. It's enough of a droop to prevent the generators from fighting each other and hunting, but it's small enough that the electrical output remains perfectly usable and highly reliable for everyone. Governing the macro grid. Now, let's shift our focus from the micromechanics of a single engine and see how this applies to the massive, shared macro grid. Because when generators are electrically tied together across hundreds of miles, the sheer rules of physics lock them together in a really profound way. There's a brilliant quote from the source material that illustrates this perfectly. Two generators in parallel can no more operate at different frequencies than the wheels of a car can turn at different speeds. They are electromagnetically locked, no exceptions. If the load increases, the entire grid slows down together. So decentralized load sharing through speed droop isn't just some good idea. It is absolutely mandatory so these massive machines don't literally tear each other apart. When you map this out on a speed versus load curve, things get really clear. Going from 0% load on the left up to 100% load on the right, the line slants downwards. The governor stabilizes the system, sure, but you'll notice the final speed is slightly lower than where it started. It successfully prevented the hunting trap, which is great, but we are left with a minor issue. We really need our grid to operate at a perfect 60 Hz, not, say, 59.5 Hz. The speeder gear. This is exactly where a device called the speeder gear comes into play. Operators or an automated control center use the speeder gear to manually or automatically alter the tension on the governor's spring. By adjusting it, you literally take that slanted speed droop curve we just mapped out and you shift the entire line upwards. This brings the grid frequency right back to a perfect 60 Hz, while still keeping the turbine fully loaded and totally stable. But there's a fascinating quirk of scale here. I love this relatable anecdote from the training document. When the little old lady in Maynooth turns on her stove, the drop in grid frequency is too small to be seen by the governors. The grid is just so incredibly massive that an individual flyball governors simply cannot physically sense those microscopic changes in load. So while the mechanical governors handle the large, sudden physical changes to keep the machine stable locally, a centralized control center monitors the macro grid frequency and constantly sends signals to those speeder gears to tweak the baseline. So how does this simple mechanical feedback loop remain the hidden heartbeat of everything from antique clocks to our modern digital energy grid? It's a pretty remarkable realization to end our explainer on. We live in this era of microchips, AI, and digital power electronics, right? Yet at the absolute core of our civilization's energy infrastructure, we are still completely relying on the fundamental physics of spinning weights, centrifugal force, and spring tension. It's a true testament to the fact that sometimes the absolute most elegant solutions are purely physical. Next time you flip a light switch, just take a moment to appreciate those spinning metal flyballs working miles and miles away to keep everything perfectly balanced. Thanks so much for joining me on this explainer.